Welcome to this short video on Fourier analysis. Now, Fourier analysis is an aside from what we are going to do in this course in classical mechanics. However, it's a topic which you will encounter again and again in many physics courses. And it's an extremely useful feature of the way we can represent a function which is periodic. So as you can see here, we have defined a function f with uppercase letter f, which repeats itself after a period t, and where this period is defined by 2 pi divided by the applied frequency. So this is a typical example of a situation which we encounter with oscillations, which we have studied till now. And when this function repeats itself in a periodic way, what Fourier's theorem says is that we can approximate or actually represent this function in terms of an infinite series of cosines and sine functions multiplied with some coefficients a of n and b of n. These coefficients can be determined if we know the shape of the functions f of t. And the way we determine these coefficients is to use properties of sines and cosines, which are called orthogonality. So cosines and sines are functions which belong to the class of orthogonal polynomials, which means that if we are going to take the integral of cosines and sines for the period for which they are defined, depending on the values n, which you see now in these arguments for cosines and sines, we may get something which is 0 or non-zero. So this is an important feature, the orthogonality of the polynomials which are being used. So Fourier's theorem plays a central role, in particular when we are analyzing oscillatory motion or systems which exhibit oscillations. So for those of you who will continue with a major in physics, you're going to encounter Fourier's theorem and what we call Fourier analysis and Fourier transforms again and again. And it's an extremely useful tool. So just to demonstrate the usefulness of that, let's go back to the Jupyter notebooks from week 11, when we wrapped up our discussions on oscillations. The code you see here is an implementation of a square wave, which has been generated using the functionality included in the SciPy Python package. And it has a period of tau, which is equal to 0.2. In this specific case, we're using 500 points. If we use less points, the curve is going to be look less like a square wave here. So I need something like roughly 500 points to get this nice representation of a square wave here. Now, it sounds a little bit counterintuitive that we can represent such a square wave function in terms of an expansions of sine and cosines. But let's see how we can do that. So if you follow down a little bit here, the slides from week 11, and you scroll down a little bit, you will see an implementation of exactly what we are saying now. So we are expanding this square wave, which we have generated here. So you can see the square signal is generated here. And then we are performing a Fourier series analysis, and we're going to calculate these coefficients, which you see here, an, and the coefficients which we mentioned in the Fourier expansion. And in this specific case here, we have a mathematical representation of the square wave functions in terms of sines and cosines. And there are some specific coefficients which we are going to derive a little bit later. Now, if you do that and you make the plot, you will see now that there is there's barely possible to distinguish the blue line, which is a square wave signal. You can see some bluish color here, and the orange line, which is now the representation in terms of Fourier's theorem. So this is an amazing result, and it sounds a little bit counterintuitive that we can represent a square wave signal in terms of an expansions of sine and cosines. But this is exactly what Fourier's theorem is saying. So let's go back to the whiteboard and look at the basic ingredients which we need to have in place in order to understand how we can use Fourier analysis in the representations of forces or functions which apply to the system in terms of sines and cosines. This turns out to be extremely handy, because if you now want to solve a differential equation like we solved for the oscillatory motion, you can expand such a force, which is not given in terms of a sine and cosine, but is periodic, so it means it repeats itself. You can expand these functions in terms of sines and cosines. And that's extremely powerful. And you can actually solve differential equations and partial differential equations for such types of applied forces to a system which exhibits then oscillatory motion. So let's see the basic mathematical ingredients which are needed in order to understand how we can use Fourier analysis and Fourier's theorem on oscillatory motion. And you will find this an extremely powerful technique. We are not going to use this much in this course, because for some of you, this may be a little bit on the side or beyond what you have had in mathematics courses. But our hope is that by seeing this, it's something which you will, in later physics courses and mathematics courses, recognize and see that, hey, I can actually use this theorem and Fourier analysis to represent a given force which is applied to my system, as long as this force exhibits some periodic behavior. So let us take a look at the mathematical properties of Fourier series and the Fourier analysis. So we have stated that if we have a periodic function, we can represent that one in terms of a series of sines and cosines. You can actually represent any type of functions in terms of these cosines and sines, as we will see a little bit later here. But the basic recipe, which is now needed in order to find these coefficients a and n, a of n and b of n, is to use the properties of orthogonal polynomials. Now, just to quickly remind you of what we actually mean with orthogonal polynomials, let's look at a well-known example here. Suppose we have defined x in between -1 and 1, and then we have a series of polynomials which are orthogonal. So let's label these polynomials as a polynomial of degree n, as a function which is given by this Pn of x. So this is a set of orthogonal polynomials. And normally these polynomials are normalized, which means that when we now integrate these polynomials from -1 to +1, they are normalized to 1. The basic property now is if I take -1 and integrate up to 1, and I have a polynomial of degree n of x, of Pn of x, and multiply that with a polynomial Pn of x, this is actually 0 if m is different from n. So it's only non-zero, and if it has been normalized, it's equal to 1. So it's only non-zero in case m is equal to n. So let's look at an example. So suppose now that we want to integrate a polynomial of degree 1. So we take this polynomial a1 of x. So that would be this polynomial here. So we put m equal to 1. So we have x to the power of 1. And we multiply that with a second order polynomial, which has a coefficient a2, which we haven't specified. And this is now multiplied with a second order polynomial. We have, in these cases, we have defined the intercept to be 0. And for the second order polynomial, the first order term is actually equal to 0. So this is an example of a first order polynomial multiplied with a second order polynomial. And then we want to calculate the integral. So this gives us simply a1 times a2. And then when we are integrating this up, this is going to give us 1 divided by 4, obviously, because we are missing a factor of 4 here. When we take the derivative, x to the power of 4 from -1 to 1. And this is actually equal to 0. So this is a pretty simple example of such a polynomial. If we now look at sines and cosines, which are the polynomials which are used in the Fourier analysis, we would now define x as a function between -pi and pi. Then, if I now calculate the integral from minus pi to pi, and I take a sine function with m times x and multiply that with another sine function, but now with n times x, what you will find then is that when you integrate this function, you will find these functions. What you will find then is that this is 0 unless m is equal to n. So this is going to be equal to 0, and it's easy to show that. So I leave that as an exercise to you, unless m is equal to n. Similarly, we can do the same thing with cosine. So we would have a polynomial of cosine with m times x multiplied with a cosine of n times x of d of x, and this is also 0 unless m is equal to n. Now, the other thing which we can do is to calculate a similar quantity with sines and cosines. So if we now look at minus pi and multiply sine of m of x times cosine of n of x, of d of x. Now this integral, now I'm going to write it out for you, is going to be given by sine squared of a of x divided by, sorry, I just have to, I'm going to rewrite it in a slightly different way. What we are going to get is the following result. So if we now keep this function, let's now, so this is actually, let me just quickly rewrite it by putting m equal to n. This is now going to be given by an integral, which is given by 1 minus cosine of 2 times m times x divided by 4 from minus pi to pi. And even in the case when m is equal to n, this is equal to 0. If m is different from n, this is also going to be equal to 0. And you can see that if you take the general case with m different from 0, and we take a sine of m of x, of cosine of n of x, of d of x, and we look at the case where m is not equal to n, this integral becomes equal to minus a half over cosine of n minus n multiplied with x divided by m minus n plus a cosine of a plus m plus n times x divided by m plus n, and this is now given by the defined by the limits from minus pi to plus pi. And you can see when you insert these numbers that this is also equal to 0. So if we have a sine times a cosine, this is automatically equal to 0. So one way to view this is that when you integrate it from a minus pi to plus pi, or a negative value to a positive value, and you look at a function which is now anti-symmetric, like sine, multiplied with a function which is symmetric. When you integrate this up, this becomes a function which is now symmetric. And since it's symmetric around 0, the final value is always going to be equal to 0. So these are very important properties of sines and cosines, which are actually used when we now are calculating the specific coefficients which we need for the Fourier analysis. We can now use these properties of cosines and sines to actually represent this function f of t using Fourier's theorem, an expansion in terms of sines and cosines, and using the orthogonality of sines and cosines, we can find these coefficients a of n and b of n. So let us rewrite a given function f of t now in terms of the Fourier expansion. So we start with an n equal to 0 to infinity, and then we had an a n. This is the way we wrote the theorem, times t plus a b of n of sine of n of omega t. So this is simply just stating that we can now represent this function in terms of an expansions given by cosines and sines, where we have two unknown coefficients, a of n and b of n. Now, in our case, in the previous case, when we looked at the integrals, we had defined x to live between minus pi and pi, but there's nothing now which hinders us to introduce the period. So we could now, by introducing the period of 2 pi divided by omega, we could change the integration domain, which now goes from x. It could now span from minus t divided by 2 up to t divided by 2. So that gives us a full period of 2 pi divided by omega. And in our case, this is going to be equal to minus pi divided by omega up to pi divided by omega. So this is just a change of variables. And if I do that, then I can actually replace my previous argument, which was given by x, and I can now replace that one in terms of n times omega times t, which is what we have here. So the change which I made here is reflected in the fact that now I'm not defining a variable x which goes from minus pi to pi, but I'm actually changing it into a new variable which is going to be given by t, and t now is defined to live between this minus t half, which is our period, up to t half. So that's a full period. That means that I can now rewrite my function which I had in terms of, I can rewrite it in terms of 2 pi divided by t, or I can just simply keep this omega here. Now, the question is, how do we find these coefficients a of n and b of n? So how do we find b of n and a of n? The way we are going to do that is simply by multiplying f of t with either a cosine or a sine function. So the first thing we're going to do now is just simply to multiply on both sides with cosine. So we're going, and then we integrate. So multiply with cosine on both sides. So we're going to put in a cosine of n omega times t on both sides. And now we are aiming at the coefficients a of n on both sides, and integrate from minus t divided by 2 to t divided by 2. So if we do that, then we are going to get the following thing. So we are assuming now that this n is larger than 0. And we are going to look at the case where n is actually equal to 0. That becomes a special case. So what we would have then is something like this. So we get an integral from minus t divided by 2 here up to t divided by 2. So we have our function f of t multiplied by cosine of n of omega of t dt. So if you now have a mathematical expression for this function f of t, you can actually find the representation of these coefficients a of n in terms of the specific function we're looking at. So this means that what I have now is a sum from n equal to 0, and then I have an integral of minus t half times t half. And remember now that I can actually skip the sine part, because we already said that the sine part if I multiply sine with cosine and I integrate, this is equal to 0, irrespective of the value of n and n. So I only need to look at the cosine part here. So I have an omega t multiplied with a sine, a cosine of n of omega t multiplied with these unknown coefficients a of n, and then this is integrated over dt. And now I can use the orthogonality of the polynomials, and what I get then is that this is simply equal to, when I'm now using the orthogonality of the cosine functions, so this reduces to, obviously n has to be equal to n. If it's not equal to n, then this integral will be 0 due to the orthogonality of the cosine functions. So what I'm going to find then is that this is simply equal to t divided by 2 multiplied with this coefficient, this specific coefficient a of n. And n has to be equal to n. So if I bring everything together, then what I have is that a of n is equal to 2 divided by t. And I have an integral from minus t divided by 2, t divided by 2, and then I get my function f of t. And I'm assuming now that this is a function which I can represent in some kind of mathematical form. So it could even be just a first order polynomial like x, or it could be x squared, it could be a cosine function, could be a sine function. If it's a sine function, this is actually going to be 0. And then I would have a cosine of n omega of t of dt. And then I have an expression for the coefficients a of n. Now I can do exactly the same thing with the sine part. So if we just go back here again, and instead of multiplying on both sides with cosine, I multiply on both sides with sine, then I can find the coefficients b of n. So b of n is going to be given by 2 divided by t of minus t half, so t half here, and this is multiplied with a function f of t, and multiplied again with sine of n of omega t dt. So this is pretty powerful. So by simply multiplying with cosines and sines on both sides of the equation for f of t expanded in terms of sines and cosines, I can now find these coefficients. And clearly, depending on the mathematical form of f of t, this can be an integral which is easy to evaluate, or it can be a little bit more complicated to evaluate. But in most cases, we can actually evaluate this integral and find analytical expressions for these a and n and b of n. That means that what I also can do now is to find this coefficient a of 0. So in the case where n is equal to 0, so one thing we will see is that the sine part disappears, and this is going to simply be given by 1 divided by t. It's actually not so difficult to show that. And again, I leave that as a small exercise to you folks to actually find this of d of t. So this is pretty interesting. Now, let us now think of a function f of t, which is just given by t. So this would be an example of what we might call a first order polynomial. Now, this is a function which is, in principle, it's anti-symmetric when you look at the function around 0. So if you take the value of the function at 0, it's obviously 0. If you then take a positive value for t, this is positive. So if I put t equal to 1, I get plus 1. If I take t equal minus 1, I get minus 1. And we say that this function is anti-symmetric. It has the same absolute value, but it has a different sign. If I had had t squared, this would be a function which would be symmetric around 0. Now, we know also that the sine function is a function which is anti-symmetric. So if I have an anti-symmetric times an anti-symmetric function, that becomes a symmetric integrand. And when I integrate that up, that's going to give me an integral from minus t half to t half, which is non-zero. So in our case, if I look at this specific function, I can now find the Fourier coefficients. So what we're going to see then, for this specific function, this example here, is that an is going to be equal to a0, and that's going to be equal to 0. And the only coefficient which is going to be non-zero is going to be our coefficient b of n. So b of n is in this case going to be given by an integral which goes from 2 divided by t, and from minus t half up to t half. And then I have t times sine of n of omega t of dt. So this is the integral which I need to evaluate. And what we are going to find then is the following. So we are going to find that this variable b of n is going to be given by 2, when I perform the integral now, it's going to be given by 2 times minus 1 to the power of n plus 1 divided by pi and multiplied with n. So it means now that I can expand this function t in terms of a Fourier expansion. So my t now is going to be given by a sum which goes from n equal 1 to infinity. So I don't have an n equals 0 term. And with that term there, I'm going to have something which now runs like 2 divided by pi times n minus 1 of n plus 1 and multiplied with a sine of n of, this is an n of omega of t. Actually, in this case, I'm going to put omega equal to 1 in this particular case here. So this is simply going to be given by n equal to 1 infinity of 2 divided by pi of n minus 1 to the power of n plus 1 of sine of n, and I'm going to change it a little bit, so it's going to be n times pi times t. So this is the expansion for t in terms of a Fourier series, which is now a collection of sine functions which go from n equal 1 up to infinity. So this is extremely powerful. I have actually represented a function t in terms of a Fourier expansion. Now, why is this interesting? It doesn't sound like a useful thing immediately. Now, it becomes useful now if we are looking at a differential equation. Suppose now that we go back to the differential equation for harmonic oscillations. So we have a harmonic oscillation. And when we set up the equations for harmonic oscillations, what we had done was to scale the equations. So what we had was a d of y. So let's look at this function y here, which is our specific position of the object which is oscillating back and forth. So we had a dimensionless time. We had a term 2 gamma, which now represented a damping factor. So we have a d of y of d tau. So tau is now our dimensionless time. We can replace that with t. There is nothing which hinders us to relabel tau in terms of t. And then we had plus y here. And this was often given by some force f of t here. So this is our f of tau. So there is nothing which hinders us now to just go back to t. So we can equally well do that. So t goes to t, tau goes to t. Now let's now look at a case where we have simply put gamma equal to 0. So we have no damping. So this sounds a little bit strange. So we have an object which oscillates back and forth without damping, and then we put an external force on top of it. So this means that we have a differential equation, which in a more compact form looks like this. We have the second derivative plus y, and this is equal to this function f of t. So let's now suppose that this function is actually equal to t. Let's just assume that. So this is now our differential equation. And we can now rewrite the right-hand side in terms of this Fourier transform. So we have a sum from n equal 1 up to infinity. So we have these factors which we have in here, which go like 2 multiplied minus 1 of n plus 1 divided by pi times n. And this is now multiplied with a sine of n times pi times t. So what we could do now is simply to say that since this is now given in terms of sine functions, we can guess on a solution y of t, which is given by some specific coefficients. And let's just call these coefficients for c. This runs from n equal 1 up to infinity. So I take a c of n and multiply that with a sine of, and then with an n times pi times t. Then I can take the second derivative. So if I do the second derivative of this function, this is just going to be given by n equal 1 to infinity. I have this unknown coefficient c of n, and this is multiplied now with minus n squared times pi squared. So I'm taking a derivative, and I'm getting sine times n times pi times t. So what I do next now is simply to equate the different terms in the sum. So if we now look at what we would have on the left-hand side. So what I'm simply going to do now is to plug this one into the left-hand side. And I'm going to plug this one into this equation for the second derivative with respect to time. And I'm going to equate the terms in the series. So that means that what we get now is the following. So if we pick a specific coefficient n, we take a specific value. If we take this specific value, what we end up with now is the following. So we have this minus n squared times pi squared. And then we have the expression here, which is simply plus 1. So I have a plus 1 multiplied with this unknown coefficient c of n. And these are equal to 2 divided with pi and divided with n, multiplied with minus 1 to the power of n plus 1. And now you see that I can easily rewrite everything here. So I get an equation for c of n, which is going to be given by 2 divided by pi times n. And then I have 1 minus n squared or pi squared multiplied with minus 1 to the power of n plus 1. Then I can plug it into the equation again, and then I have my solution. So this is now my particular solution to the differential equation in terms of a sine expansion. So I'm going to get my solution now as a function which is given by n equal to 1 up to infinity. And then I have this coefficient c of n, which is 2 divided by pi times n, 1 minus n squared, pi squared, multiplied with minus 1 to the power of n plus 1, and finally multiplied with a sine of n times pi times t. So Fourier analysis is an extremely powerful way to solve differential equations related to oscillations. So we can find, by using the orthogonality of the cosine and the sine functions, we can find these coefficients a of n and b of n. So we can now, if we go back a little bit, we can find the coefficient b of n. In this specific case, since we had an antisymmetric function, it's only the sine part which is involved. If we had a function which would be symmetric, we would most likely end up with a cosine part. And then we would have coefficients a of n and a of 0, which may not be equal to 0. But what we can do is we can always calculate these quantities here, this integral. So sometimes the function f of t is a little bit more complicated, but in general, we can actually even calculate these coefficients analytically. When we have that coefficient, in case we now have a differential equation, which is given by this simple example here, where the applied external force is given by this first order polynomial, then we can now equate the terms on both sides, on the left-hand side and the right-hand side, and we have immediately the particular solution. Now, going back to this square wave function, that requires a little bit more complicated sine and cosine expansion, but we can expand that in a basis of sines and cosines. And then we can find the expression for this f of t in an expansions of sines and cosines, and then we can solve these differential equations. And that's the strength of the Fourier analysis. So we can express a function like this f of t here, which sounds complicated, like this square wave function. It could be a triangular wave function, or any other type of periodic function which you can produce in the lab, which is not easily represented by, let's say, a nice function like a sine or cosine. But we can use Fourier's theorem and simply represent a complicated function f of t in terms of a series of sines and cosines. Now, going back to one of my favorite examples, you could now think of you riding on a gravel road and you hit a washboard. Now, the washboard would be something which you, if you studied a little bit closer, repeats itself in a very regular way, and then it stops. So when you're coming with your bike here, so this is my bike here, and then you hit the washboard, what you could do now is simply to model this washboard in terms of a specific function, and then expand that in terms of a Fourier series. Then you can plug this into the differential equations and figure out what is the optimal way to reduce your impact as a cyclist with this washboard on a gravel road. Alternatively, you can think of other situations where you want to dampen the oscillations which could kick in case you hit a rough surface or other kinds of problems which involve oscillations. So Fourier's theorem is extremely powerful, and you're going to meet it in many, many physics applications, from electronics, electromagnetism. You're going to see this again in quantum physics, Fourier transforms, the way to calculate them. You see you have an infinite series. There's actually one of the top 10 algorithms in numerical mathematics, which is called fast Fourier transforms. Now, Fourier transforms are used in order to calculate eigenvalues in quantum computing algorithms. So you're going to meet this mathematical method again and again in your physics studies. So this was meant as a teaser. We're not going to use it very much in this course, but it's important to have seen it because you're going to meet it again and again. And this concludes this video on Fourier transforms.